Hi, this is Alex from devstories.eu. SunPy, Solar Data Analysis, Episode 8 of 12. You load a beautiful piece of solar data, render the image, and end up staring at a totally black square with exactly one bright white pixel in the corner. Your data is fine, but your dynamic range is completely hiding it. Fixing this is what publication quality map visualization is all about. When developers first try to visualize a SunPy map, they often pull the raw data array and feed it straight into a standard matplotlib image show command. This renders the pixels, but it drops all physical context. You lose your coordinate system entirely, and your axes default to simple array indices. SunPy resolves this with a built-in plot method directly on the map object. When you call plot on your map, SunPy automatically provisions a world coordinate system axis, known as a WCS axis. This ensures your tick marks accurately represent physical units on the sky, such as arcseconds. You do not have to abandon matplotlib layouts to use this. You can create a standard matplotlib figure and add a subplot. The trick is to pass the map's WCS object into the projection argument of that specific subplot. Then you simply pass that specific axis back into the map's plot method. This integration gives you the precise formatting control of matplotlib while keeping the strict spatial awareness of SunPy. Now back to that black square with one bright white pixel. Solar images have extreme contrast. A solar flare might be tens of thousands of times brighter than the faint coronal loops right next to it. If you map the raw data values linearly to a visual color scale, the flare claims the top end of the scale, and everything else gets crushed into shadow. Here is the key insight. You must compress the dynamic range before rendering. You do this in two steps, using clipping and normalization. First, use the clip interval keyword argument in the map's plot method. Instead of letting one ultra-bright outlier define the maximum value of your color scale, you can supply a tuple representing percentiles. Setting the clip interval from 1% to 99.5% forces the plot method to ignore the dimmest 1% and the brightest 0.5% of pixels when calculating the color boundaries. Clipping instantly cuts through the glare of extreme outliers. Second, even after clipping, a linear scale usually leaves quiet regions too dark. To fix this, import the LogNorm class from matplotlib colors. You pass an instance of LogNorm into the norm keyword of the matplot method. Applying a logarithmic stretch mathematically amplifies the faint structures in the dark regions of the image, while compressing the visual differences in the brighter regions. When you apply LogNorm, those faint sweeping coronal loops emerge clearly from the background. Finally, set the correct visual palette. SunPy automatically registers standard solar map colors within matplotlib. By passing the CMap keyword argument to the plot method, you can specify an exact instrument channel. Passing a string like SDOAI171 applies the precise gold-colored palette the scientific community uses for that specific wavelength. Combining the built-in plot method for coordinate accuracy, clip intervals for handling outliers, logarithmic normalization for dynamic range, and an instrument-specific color map transforms a nearly completely dark array into a detailed, publication-ready scientific figure. I would like to take a moment to thank you for listening. It helps us a lot. Have a great one.